Welcome everyone to the webinar today, The Potential to Increase Soil Carbon in European Agriculture and Multifunctional Production Systems. Today we are joined by Oskar Englund. Oskar is an Associate Professor in Environmental Engineering at Mid-Sweden University. Oskar's research is primarily centred around sustainability issues concerning biomass production and land use. Today's webinar will present the findings from a recent study in which a spatially explicit model was applied on more than 81,000 sub-watersheds in EU27 and UK to explore the effects of widespread deployment of such systems. As always, there'll be a chance for questions at the end of the presentation, so please do ask these in the Q&A option at the bottom of your screen at any point during the presentation, and I will ask these on your behalf at the end. Thank you for logging in, and I will now hand over to Oskar.
Thank you very much, and thank you for inviting me to give this seminar. And I'm going to present, as you just heard, a study which we recently published. But before talking about the study, I want to talk about land. And this is the amount of land that we all have. If we would distribute all the land on Earth equally among all the people on Earth, this is what we would have: a nice little square, 145 by 145 meters. Like a third of that would be deserts, glaciers, not very productive land. A quarter of it would be forests, roughly the same amount of pasture. And then we have a little bit of grass for our lawn, perhaps, and some cropland to produce our food, and a little place 20 by 25 meters for our house and all the roads we need to get to work in our workplace, and our share of the supermarket and everything. So this is what we have. And of course, we need this land to produce the food that we need and all the other materials that we need. But as we get more people on Earth, we become more people, and we start to use the biomass from the forest and from the cropland for more purposes. We need more biomass, and what do we do then? Because we only have this square. Well, one thing that we can do is to expand, to make our cropland a little bit bigger, going into perhaps taking away some forest or making our half a cow, which is what this land is suitable for, making our half a cow a little less satisfied by having a little bit less space to move around on, or removing a little bit of our grassland. But that comes with consequences. And consequences are also, we also get consequences if we try to produce more biomass by intensifying our biomass production, trying to produce more biomass on the land that is already being cultivated. And these types of consequences, they manifest themselves in environmental impacts. And we have here, of course, everybody is familiar with climate change, and that is of course heavily associated with the use of fossil fuels. But a large share of it can also be attributed to agriculture and forestry. And to the left, we see algae blooms, and that's a result of nutrients leaching from agricultural land. And then recently, we have sort of almost discovered the last decade or so that we have a problem with biodiversity. People argue that we are in the sixth mass extinction, and that is of course something that is that can be explained by the way we use the land. So I have no idea why this slide is blue, but never mind. So basically, I mean, agriculture and forestry has caused substantial environmental impacts. And I mean, of course, there are processes to remediate this, at least in some parts of the world, but the most of those measures, they imply reducing biomass production, setting aside land, etc. And the problem is that we become more people on Earth all the time. We need to feed more people, and people also tend to live more resource intensively. So they need more biomass for that. And we also have an emerging bioeconomy that we need to supply with biomass. So we need more biomass. Are these objectives then incompatible? Because they certainly appear so. One way of addressing this problem is to focus more on multifunctional production systems. And these are production systems that provide not only biomass, but also environmental benefits in the process. And one way of doing that is to strategically introduce perennial crops in intensively managed agricultural landscapes. If we do this in a clever way, we can provide the same environmental benefits as setting aside land, but we can maintain the biomass production in the landscape. One example of a multifunctional biomass production system is to include grass or grass clover in rotations with annual crops in agriculture. And this has been done this is a traditional practice, and it's still used to a large extent in Northern Europe. And the benefits of including grass is that the root systems are so much deeper than for annual crops. And they also established for multiple years. And so we don't have to disturb the soil every single year or multiple times per year. So this has an effect on soil carbon accumulation. If we have a very highly intensive production of annual crops, we decrease soil carbon over time. But this can then be remediated by instead producing grass. And it has also been shown in many studies that the inclusion of grass in crop rotations can increase soil fertility and yields, also then for the annual crops that you rotate it with. Other benefits is that you get reduced nutrient emissions to water, and since the root system stabilizes the soil, you get a decreased soil erosion. It also slows down the flows of water in the landscape, reducing flooding events, and of course decreases the use of pesticides with effects then on biodiversity. And at the same time, you produce biomass. So biomass in combination with environmental benefits. So we asked ourselves, because we have been focusing on multifunctional production systems for quite some time now, developed a few models. We asked ourselves, but since this is working so well in Sweden and we know that the effects would be really good, what would the potential be of introducing it on large scale across Europe to remediate, because we have substantial losses of soil organic carbon on European cropland? This may be a way to remediate that while still maintaining biomass production. And here's a slide with an awful lot of information, so we will go through it slowly. What we did was to look at the sub-catchment level. We looked at 81,000 sub-catchments across EU and UK and assessed them separately. And we had two deployments now, because we wanted to understand what could a widespread deployment look like if we introduce this on a large scale. So we had two scenarios, a high estimate and a low estimate. And in each landscape, we looked at what is the current situation when it comes to soil organic carbon. If we have a large accumulated soil organic carbon losses in the landscape, our model introduces grass to a larger extent into the crop rotation. And we can see on the top left figure here, we can see accumulated soil organic carbon losses across Europe. And it correlates very well with the density of annual crop production. To the right, we see a yield model, which we also used then, because when the model had introduced the grass into the crop rotation, we also got the grass area, and then we can see, then we could calculate how much grass biomass that could be produced. And at the bottom, we see a figure showing what type of and to what extent grass was introduced in crop rotations, because that, as I just said, depends on accumulated soil organic carbon losses. In most cases, we see yellow, and that is where we have the sort of rather high soil organic carbon losses. And there we introduced a system with 2 years of grass and 4 years of annual crops. And it was implemented at 50% of the land in the low estimate. But we also tried different types of, we tried 3 years of grass and 4 years of annual crops, and 4 years of grass and 4 years of annual crops, depending on the degree of soil organic carbon losses. So what the model found was that we should introduce grass in crop rotations on a whopping 91 million hectares, to a varying degree, of course. And this means 30% of all subcatchments, and this land contains 80% of all land used for production of annual crops. So we're not talking about some small measures here. We're talking about a massive transformation of the entire agricultural system. And total area that would be under grass production in these scenarios is between 15 and 38 million hectares. And this corresponds to 13 to 35% of the total area under annual crops in Europe. So a large amounts of land. This also means that we can produce a lot of biomass, 100 to 300 million tons. And if we want to use that for biogas, for example, we could produce 140 to 400% of the total biogas production in EU. Not the latest figure, but I think you get the point that we're talking about a lot of biomass and a lot of energy from this land. And we can see here what the results is on soil organic carbon. This is by 2080. So in the long term, we get a soil organic carbon increase by 200 to 500 million tons of carbon, which is quite a lot. It corresponds to 4 to 10% of the current greenhouse gas emissions from the agricultural sector in the entire Europe. So quite a lot of carbon, and the climate benefits are substantial. But if you also consider then that we could use this biomass to replace fossil fuels, for example, by producing biogas, then we can achieve climate benefits up to half of current greenhouse gas emissions from agriculture. So that is quite substantial. If we take a look again, we can also look a little bit closer at the figures. We see the low estimate to the top and we see the high estimate to the bottom. And the colors, they show the amount, the tons of carbon per hectare in each subcatchment. And we see that there's a big difference between the low estimate and the high estimate. And that is because in the high estimate, we introduce grass to a larger extent than in the low estimate. And so in the high estimate, we can see in southeastern part of Europe, we can achieve over 10 tons of carbon per hectare. And but in the low estimate, it's typically around 2 tons per hectare or lower in most parts where these systems are introduced. And so far, so good. But then we also, because we knew that introducing grass on agricultural land does not only increase soil organic carbon, it also comes with other potential benefits. And these benefits, they depend on what type of environmental problem you have on the land where you establish the grass. Here we see 4 maps. It's to the left, we see the low estimate, and to the right, we see the high estimate. On the top row, we're looking at nitrogen emissions to water. And on the bottom row, we're looking at soil loss by water erosion. So let's start with the top row and look at nitrogen emissions to water. Because if we include grass in the crop rotations, this will be reduced. And in the high estimate, we see that there's a lot of green everywhere. And green means that we reduce the emissions more than what is needed to achieve a low level. Meaning that it sort of exceeds the mitigation needs. And this is a co-benefit. It's not something that we don't establish the grass for this reason. This is sort of something we get for free. In the low estimate, of course, since we introduce grass to a lesser extent, we see fewer areas where we sort of solve the problem of nitrogen emissions to water. But we still see that even in the darkest areas, we are at 20, 30, 40% of the mitigation that is necessary. So it's we can see a substantial decrease of nitrogen emissions to water. And on the bottom row, if we look at water erosion, this is a pretty widespread problem across Europe, primarily in Southern Europe. And we see a similar picture here to the right. We see that we introduce so much grass into the landscape, so we pretty much solve the problem with water erosion. And to the left, we see again that even though it's fewer areas where we sort of solve the problem, we still achieve 20, 30, 40% of the mitigation needs. So we see substantial benefits when it comes to soil loss by water erosion. This is something else that has been we have experienced across Europe the past years, some severe flooding events. And as I said earlier, if we have perennial crops in the landscape instead of annual crops that leave the soil bare for large parts of the year, we slow down the water flows in the landscape, and we mitigate flooding events. So this figure basically shows because we were not able to quantify these benefits. We were able to quantify nitrogen emissions to water and soil loss by water erosion and soil loss by wind erosion, but not flood mitigation. Instead, we tried to indicate the likelihood of flood mitigation by introducing grass and crop rotations. And what we see here is that there is a very high likelihood that we are able to mitigate floods in large parts of Europe, basically along all the major rivers in Europe, where we also have large agricultural areas. So the elephant in the room then. We're talking about transformation of the entire agricultural system, replacing like a third of all food production with grass. And we can't eat grass, so that's a problem. What about food production? It's quite trivial that replacing up to a third of food production in Europe will have massive effects on the global food system. Including the impact on food prices, which also means the de facto availability of food, at least in poor countries. So this is not something to take lightly. But then we can ask ourselves, how could we mitigate this? Because this looks like a pretty good idea. Well, one way of doing it is to use the grass for purposes that are currently met by annual crops. That means that if we use the grass biomass for something, then we usually use annual crops for it. Then we don't need to produce that amount of annual crops any longer. So then we don't displace the cropland somewhere else. And very interesting alternative when it comes to this is to use green biorefineries. And biorefineries are characterized by the ability to produce multiple products, to utilize different sort of parts of the feedstock for different purposes. And there are full-scale refineries in Denmark that have been developed over the last decade, where you could use grass biomass to produce a protein concentrate that you can use to replace soybean meal. You can give it to pigs, for example. And there have been trials, of course, feed trials, and the results are good. So this is a very interesting alternative. So if we then use the grass to produce a protein concentrate, then we don't have to produce the same amount of soybean meal, and then we save that cropland, basically. We reduce the cropland displacement effect. The green biorefineries can also produce biogas and fiber fraction that can be given to ruminants. The problem here I can add also is that if you focus on replacing annual crops in specific applications, such as for feed, the alternative to that would be to focus on maximizing the climate benefits, for example, by replacing fossil fuels to as large degree as possible. Then you would have, if you do that, you would have a greater climate benefit, but you would have a larger cropland displacement. So there is a sort of balance to find there. And here we can see, this is a very nice and complicated figure, so we'll take it slow. What we see here, we see six sort of matrices, and and they represent the amount of land, all land that we introduce grass in crop rotations on. And in the first case, we see here in the first step, we see the cropland displacement. In the low estimate, we replace 17% of this land. It was formerly food production or feed production, but now we produce grass on it. So we sort of displace this land elsewhere. There's an increased need for annual crop production elsewhere because of the introduction of grass in crop rotation. And in the high estimate is even worse. Then we have 42% of the land that we produce food and feed on from annual crops is displaced. There is a corresponding increased need for annual crop production elsewhere. But by introducing grass into the crop rotations, we get also yield effects for the annual crops on the land where grass is established. So we get local effects, we get higher yields, and this means that we can produce the same amount of biomass or food on less land, which decreases the need for annual crop production elsewhere. So now we're down to 10% in this case, in the low estimate, and 30% in the high estimate. Still a huge amount of land that is needed elsewhere to produce annual crops. If we want to produce the same amount of annual crops as we did before. But then in the third step, we're looking at the net effects. And here we have introduced the green biorefineries, and that they can utilize the grass to produce protein concentrate that can replace soybean. And these ones are if we use soybean from South America. But if we use soybean produced in Europe, we can add a little bit more because there are lower yields in Europe. So if we then theoretically, if we can utilize all the grass that we produce to produce protein concentrate and replace a European soybean meal with that, we would have a 3% net reduced need for annual crop production elsewhere. And in the high estimate, it's even sort of better. We can achieve a net benefit or a reduced need for annual crop production elsewhere corresponding to 5% of all these 91 million hectares that we have established grass on. And I need to stress here, of course, that these are theoretical numbers, and in reality, of course, we will not utilize perhaps not utilize all the grass for these types of biorefineries. But this sort of, I think, this exemplifies, it highlights that it's possible to use to a greater extent produce non-food crops without having substantial effects on food production, but it requires that we do it right. So, how then? As I said, this is a massive transformation of the entire agricultural system. So, we need incentives if we want this to happen. And one thing that is necessary is markets for biomass. Of course, farmers will not start to grow grass in rotation with their, well, some may actually, if they have problems with unfertile soils, they could consider introducing grass in crop rotations just to increase fertility and get the yields up. But most would not. So we need markets for the biomass. Otherwise, it would not be economical to establish these types of systems. And one way of doing that is, of course, to use green biorefineries, so that we can get a greater demand for grass biomass. The other thing we need is, because what we produce in these systems is not only grass, is also environmental benefits. And these environmental benefits is a benefit to society. And society should compensate the landowner, the farmer, for that. So we need compensation. for the soil organic carbon sequestration, but also for other environmental benefits that you produce when you establish these types of systems. So I've been even more punctual than I needed to be, but to conclude this study, I mean, we found that widespread deployment of grass in rotation with annual crops can result in substantial increases of soil organic carbon on agricultural land, corresponding to 4 to 10% of current greenhouse gas emissions from agriculture. If we also include that we could utilize this biomass to replace fossil fuels, we can achieve up to 50% of current greenhouse gas emissions from agriculture as a net climate benefit. The environmental co-benefits appear to be substantial and in some cases exceeding the mitigation needs. There is, however, a risk of severe impacts on food markets with increasing food prices. But if we can utilize the biomass in a clever way and replace soybean, for example, or other types of applications of annual crops, then we can reduce this impact on food markets, and we can even theoretically result in net cropland savings. Implementation requires markets for grass biomass, but also compensation for environmental benefits. And as I said earlier, also, this is one study in a series of studies focusing on multifunctional production systems. We have looked at riparian buffers and windbreaks using short rotation coppice, willow or poplar. And we have also a few other papers that you can read if you're interested in more to read more about this. And if you want to contact me after the seminar, you can find my email address at the bottom of this page. So thank you very much for listening.
Fantastic. Thank you, Oskar. Really interesting to see that. We do have some questions, and I would say that if anyone else does have a question, please pop it in the Q&A option at the bottom of your screen. So the first one here is, researchers found a large variation in the rate and final equilibrium level of soil organic carbon captured by introducing grassland to cropland. What average SOC benefit per hectare did you assume?
Yeah, that's very true. And this is something that I think is important to emphasize, that it is this study is associated with massive uncertainties. I can't say by heart exactly what type of, well, I can actually say that because the increases of soil organic carbon is based on the simulations, the pan-European simulations by the Joint Research Center, European Commission Joint Research Center. And so that is sort of the basis for quantifying the soil organic carbon accumulation. But I think it's a very good question. It's we have actually a PhD student now working only on trying to understand, trying to build models on soil carbon in a very small area in Sweden, and that is complicated enough. So, I mean, trying to do this on a large scale in Europe is associated with substantial uncertainty.
Perfect. Where grass is used as a biorefinery feedstock, have you assessed the overall energy return on energy invested in the resulting system? And if so, is it net positive?
Yes and yes, with a reservation that it has been a few years since I was involved in that project. So, but I am almost 100% sure that has been done with, and it has been a net
Fantastic.
positive or negative. What would it be? Net energy saving. Yeah.
Have you done any cost calculations at farm level to balance out the loss in cropland versus potential increased yield from improved SOC?
Can you repeat that, please?
Yep. Have you done any cost calculations at farm level to balance out the loss in cropland versus potential increased yield from improved SOC?
No, and that is definitely a subject for future studies, because as I was saying towards the end there, this needs to be economical, otherwise it would never happen. So these types of cost analysis have to be made. But that we have not done it. We have done in the past. We have done, of course, cost calculations, but not associated to this particular scenarios.
This question's related to that actually. Who specifically is paying for the SOC increase? There is substantial pressure on producers and consumers, and no one wants to be paying more.
I think that the societal benefits should be paid for by society in some way, in one way or the other. And this is something that has been increasingly discussed now in the policy development at the EU level. There are policy instruments popping up that creates opportunity for farmers to get financial compensation for providing environmental benefits. So these types of policy instruments are popping up, and that is, of course, one alternative that I think is very promising. But then, of course, there are different ways of providing sort of an financial benefit sort of for the producer. It can also be covered by the consumer, for example, using certification. But I think that's a little bit far-fetched in this case. I think in this case, what I see as most logical would be that it's included in the agricultural policies. That you get basically compensation from society if you do something that is beneficial for society on your land.
Great. If 91 million new hectares of grass are planted, and we assume that it will lead to a net increase of SOC, how are the SOC levels going to be measured and monitored over time?
Do you mean so to verify that you actually deliver the benefit that you have promised? Yeah, that's an excellent question, and I have there are of course standard ways of measuring soil organic carbon on cropland. So of course this is, but you're pointing to something interesting here. If we want to have these types of compensation systems where you get compensation for environmental benefits, it's not enough to have this sort of pan-European modeling study to base the compensation levels on. It must be based on the actual benefits on the land where you are doing some changes. So we need better tools to understand or to sort of predict what benefits we can get on specific sites, on specific fields, in specific landscapes, in order to determine maybe compensation levels, but then also to follow up and to see that we actually deliver what was expected.
Great. This one's related to cost again. Interested to know, with biorefineries, how important proximity to farm is in achieving the greenhouse gas benefits, but also making it cost effective.
Oh, I'm sorry, I missed a few words in the middle. Can you repeat, please?
Yep. Interested to know, with biorefineries, how important proximity to the farm is in achieving the greenhouse gas benefits, but also making it cost effective.
Yes, quite close, actually. I don't remember exactly what was concluded, but this is not, we're not talking here about big transportation costs are a substantial part of the total sort of cost effectiveness. So you can't have, we shouldn't rely on very, very large biorefineries and very few of them, but instead smaller and more distributed biorefineries to get that cost down. But I can't say exactly in the cost calculations that have been done. It has been shown that transportation cost is crucial, but I cannot say exactly what the threshold is when it becomes unprofitable, because I don't remember that.
Okay, perfect. And the final question is, has this been trialed anywhere? And I guess if it hasn't been, are there any plans to trial it anywhere?
Yes, this has been tried in Denmark.
Okay.
I think over the past decade or so. At first, a pilot plant, and then it was scaled up to a demo plants, and so this has been tried, and now it has gained quite a lot of interest in Denmark, and but not for the sake of increasing soil organic carbon, but for the sake of reducing nitrogen leaching, because in Denmark they have huge problems with nitrogen leaching. So, and there has been then talks about how to reduce this, and one way of doing it is to, of course, to produce more grass. And then people started to think about, but what to do with all the grass? And then some clever people came up with the idea of using it to produce a protein concentrate. So it's not for the same reason as we present here, to increase soil carbon, but to reduce nitrogen leaching. But there's been quite big interest for this. I think there are several new biorefiners planned or under construction already in Denmark. So this is definitely something real.
Mm-hmm. Fantastic. Really interesting presentation. That's it from us today, attendees. Thank you for logging in. I hope you found that beneficial and informative. Don't forget to record your attendance at the webinar on the IES CPD tool. You can do that by logging into the members area. This webinar has been recorded and will be made available on the IES website and YouTube channel. Our next event is tomorrow, and it's an IEQM webinar on schools air quality monitoring for health and education. Again, it's a free online event, so visit the IES website to register. I'd just like to say thank you again, Oskar, and thank you again to the attendees for watching. Thank you.
Thank you so much. Bye-bye.